the reciprocal function? Because y equals the reciprocal of x. Okay? It's actually rational. And do you remember what the word rational means in math lingo? Rational numbers. A rational number is just a fraction. Any number that can be written as a fraction. Okay? So a rational function is any function that can be written as a fraction. And a rational function, there's a couple of ways it can look, but if we look at our, a rational function has the form p of x over q of x, okay, where p of x and q of x are polynomial expressions, okay? So you've got a polynomial over a polynomial. The real deal is a rational function is one where x is in the denominator, okay? A rational function has an x or more than one x in the denominator. And that changes everything, because as soon as you put an x in the denominator, you don't know the value of x. X is a variable. So the one thing we can never do is divide by 0. So that gives us asymptotes. That's how the asymptotes happen that we'll see in a moment. Okay? So one other thing I'm just going to say to you also, should have added to the notes. Okay, so here, this is just p of x, q of x, right? They just represent two polynomials. Okay? I'm just going to write up here too. A rational function may also be given to you in this form. Okay? So you can be given to polynomial over polynomial, or it could be given to you at like this: y equals a over x minus h plus k. Does any of that look familiar to you? What do you think the a, the h, and the k are? I guess I could give a b as well, right? Sorry, Johannes? Yeah. Sometimes, like this, we can always use transformations to graph functions. So it looks slightly different. Is there an x on the bottom? Yeah. But usually just it's been kind of transformed from this form to this form, and I'll tell you how we do that later on. These are both, if the definition of a polynomial function is a function with an x on the bottom, does this form have an x on the bottom? Yeah, right? Does this form have an x on the bottom? Yeah, it's a polynomial. So they both have x's on the bottom, they both qualify. They just look like they're in slightly different forms, but that's not unusual for you, right? You've seen that already. You're quite familiar with that with this, right? I could give you a quadratic in this form, right? That's a quadratic, and it graphs like that. I can give you a quadratic in vertex form, right? Graphing form. Same with, that's the same thing with rationals. So with quadratics, these are both positive quadratics, right? For a polynomial, it might look like, okay, here's a polynomial on top, here's a polynomial on the bottom. That's one type of rational function, or I can give it to you like this, right? They might be different rationals, but see what I mean? This is kind of a graphing form. Things are really easy to see, just like this is. Whoops, put a 12 here. Really easy to see what's happening here. This is easy to see. This actually, we're going to decode it. We're going to start decoding them today. This is actually pretty easy to graph from too. This is a little harder to graph from, wouldn't you say? The only thing you know for sure is the y-intercept is 3. I probably couldn't factor this because it's not factorable, but you know what I mean? There's different forms of quadratics. so you can graph from either form that you're given. All right, so let's see what the parent graph looks like. I know that you're all familiar with this one, but we're going to revisit the parent function just to get another refresher on how those wings happened and how an asymptote is created. All right, so this is the reciprocal graph. This is the graph of y equals 1 over x. Okay, so x is on the bottom of a fraction. That's important because I can never have a 0. I can't divide by 0. Dividing by 0 doesn't exist. You get error messages. Algebraically and graphically, you get asymptotes, meaning I can't reach that value. So how does that happen? Another way to think of 1 over a number is, like if I say, for example, let's pick some numbers. I'm going to put 0 smack in the middle. So let's pick a 1, a 1/2, a 2, and let's do a 4. Okay? All right. So let's start over here. What's 1 divided by 1? Like if x is 1, y equals 1 over the number. So it's just 1, right? What's 1 over 1/2? It just becomes 2, right? 2 over 1. Like that's why reciprocal function is a nice name to call it, because whatever the x value is, it's just the reciprocal of that number, which is y. So this is going to be 1 over 2 and 1 over 4. Is everyone okay with 1 divided by half just becoming 2? Because the reciprocal of a half is 2 over 1 or 2. That's just dividing by fractions, right? We never really divide by fractions. We multiply by the reciprocal. So that's how we got the reciprocal of a half is 2. Okay, now the problem comes 1 divided by 0. I hope I left my calculator here, and I don't think I did. Can I borrow your calculator, Joanna? I always forget to bring it. Okay. Now you learned this a long time ago. 1 divided by 0? No. Okay. 1 divided by 0. So Joanna has one of these nice calculators. You can see exactly what I did, and we get an error message. Okay? You can have 0 in the numerator, right? That's fine. 0 divided by 1, that's cool. That's 0, right? Because that makes mathematical sense. 1, to work backwards to check the answer, 1 times 0 gives me my starting point 0, right? If I have 1 over 0, though, some might be tempted to think, oh, the answer is 0 again. But I'll show you that it can't be. Because that would mean that 0 times 0 equals 1. And that doesn't work, does it? So there's no answer. We say, well, you can say no answer, no solution, undefined, that's another way, that's a better way to write it, D. Undefined. Or actually, sometimes you'll see this. You'll see 1 divided by 0. You can either say undefined. You might also see this. Infinity. It's kind of, and we're going to see how that happens, because that's what happens to the value that we're seeking. It just approaches infinity. It never ever reaches a value. It just keeps approaching infinity. But 1 over 0, we're going to say it's undefined. Okay. I'm just going to keep your calculator for a couple minutes, Joanna, if that's okay, all right? Okay, so let's work backwards. So this is undefined, and we're just going to say undefined here. Okay? All right, let's work some negatives. I guess we'll do our counterparts. -1, -1/2, -2. Okay, well, and this is interesting too. What's the reciprocal of -1? 1 over -1 is -1. The reciprocal of -2 over, or -1/2 is -2 over 1, or just -2. And this is -1/2. Do we have any invariant points? Do you remember what invariant means? Like, the reciprocal of 1 stays 1, the reciprocal of -1 stays -1 too. That's kind of nice. That helps us graph. Okay, so anywhere that x is undefined creates an asymptote. So that's what I'm going to write in here. Where x is undefined creates I'm going to erase my little division here. Okay, so where x is undefined, x is on the horizontal axis, but x being undefined, that whole value of x is undefined. So we say it creates a vertical asymptote. So vertical asymptote at, in this case, where x equals 0. So asymptotes, if you've had some experience with asymptotes, how we indicate them in a graph in math class is, it was traditional to use a red pen, I don't know why, but you can use a pencil. So wherever x is, here's where x is equal to 0, right? So I create this, and asymptotes are created using dotted lines. That's the one must. You can use a pencil or a pen, but it has to be a dotted line. It's a line, so I'm going to put arrowheads indicating it goes on forever and ever. Okay, so now I'm going to do some point plotting. We're going to see what this graph looks like. So, where x is -2, y is -1/2. So here, where x is -1/2, y is -2. 0 is undefined. Negative and 1 has a value. Okay, so that's my graph. Now what's going to happen here? What if I took another value, like what if I said x was -1/2? What if I snuck another value, like if I extended my chart a little bit? What if I said x was -1/4, sorry? Y is going to be -4, agreed? So a -1/4, y is going to be -4. As x gets smaller and smaller, like if I just think in the negative world, x gets smaller and smaller and smaller, what happens to y? What does reciprocity mean? See, when x gets smaller, let's start here. X has a 4, and then it's going to get to 2, then it's going to go to 1, or go to a 1/2. So x is getting smaller here in this section, right? Okay. What's happening, or I guess x is getting larger. We'll say x is getting larger here. What's happening with y? Y is getting smaller, right? It's actually moving towards 0, right? How about this? As x approaches 0, what's happening with y? It's going, let's try this. I think it's getting, well, let's try this. Let's do the negatives again. As x is approaching, as x is going from -2 to -1/2 to -1, it looks like x is approaching 0, right? As x gets smaller and smaller, if I'm approaching, my x values are getting smaller and smaller, y should get bigger and bigger, right? And sure enough, it is. As x is getting bigger and bigger, like look at my pencil, as x is traveling through the bigger negatives, y gets smaller. Okay, now the interesting thing is, on this whole half of x, this is the whole half of x, x is negative here, right? X is negative on this side. on this side of the asymptote. So y also must be negative. Do you agree with that? If x is negative, y has to be negative, right? Look, if x is negative, y is negative. Just reciprocating a number doesn't change its sign. So remember that. Wherever x is negative, y is negative. Where x is positive, yeah, y is positive. And your vertical asymptote basically creates those positive and negative areas. If you have a vertical asymptote, one side of your graph will be positive, one will be negative. Okay? You can't have positive and negatives on the same side of a vertical asymptote, or it won't be a function anymore. It won't pass the vertical line test. Like if I have a section of my graph down here, I can't have another wing up here, can I? If it's a function. Agreed? And why? It won't pass the vertical line test, right? So if you have a section of your graph that's negative, you're not going to have a positive right above it. It's got to be one or the other. So vertical asymptotes kind of section your graph off into positive, negative sections too. Okay, so as I move down smaller and smaller to x, y gets bigger. As x gets bigger, y gets smaller. Same thing's going to happen over here, right? I have a point at 1, 1. When x is a half, y is 2. If x is a quarter, y is going to be 4. And it's just going to keep traveling up and up. As x gets larger, 2, y will be a half. When x is 4, y is a quarter. Now this is interesting, because an asymptote is defined as a value of x or y that the graph approaches and never reaches. So x equals 0 is a vertical asymptote. Would everyone agree with that? Now, doesn't it appear that the x-axis itself is an asymptote? Wouldn't you say that this is also an asymptote? If I told you an asymptote is a value that the graph tries to reach but never ever does? Because y can never equal 0, right? So I'm also going to put this in. My horizontal asymptote occurs also at y equals 0. I'm just going to put a note in here. Note that y equals 0 is also an asymptote. Because y can never equal 0. Okay. Example, well, let's put a 0 in for y. Given y equals 1 over x, let's replace the y with 0. Replace y with 0 and solve for x. Like I'm trying to prove to you there's no x-intercept, right? There can't be if this is an asymptote. So what happens is I put a 0 in for y and I try and solve for x, okay? Then what happens? X, if I'm cross-multiplying to solve for x, what would I do? I'd multiply x times 0 equals 1. Anything times 0 equals 0. So then I get a statement that 0 equals 1, which is false, right? That's a false statement. So, not possible. That means there's no x-intercept. We have a vertical or a horizontal asymptote at y equals 0. So you can tell very quickly by looking at the denominator, what values of x are going to create vertical asymptotes. Sometimes it's a little harder for students to see the horizontal asymptotes, and in this case we graphed it first. Then it became obvious, oh, this graph is never going to cross the axis, it has no x-intercepts. I guess there is a horizontal asymptote. So then that's what happened. But I'm going to show you today that I can tell, or there will be a way for you to, in a few short minutes, there's going to be a way for you to quickly look at the equation that you're given and determine if the graph has vertical and horizontal asymptotes, pretty much like that. Okay, so that's what we're going to learn today. Let's fill in the rest of this, but everyone knows this graph, right? Yeah. Now you might know a little more about it, I don't know. What's a non-permissible value? That means we're looking for values of x. So x can never equal 0. Right? It's the values of x that we 0 at the bottom. Equation of the vertical asymptote, we say x equals 0. Equation of, so this is the equation of a vertical line, right? The equation of the horizontal asymptote, so the horizontal asymptote is y equals 0 as well. Notice that you're asked for equations of asymptotes, so they have to be given in the form of a line, right? X equals 0, y equals 0. What's the domain? Okay, there's a couple ways we can do it, right? I guess we could do this. Negative infinity to 0, both of them not included. Union, 0 to infinity. That's one way. The other way you can do it is this way. You can do this. You can say XER like that, because x can be everything except x can't equal 0. You can do it that way as well if you want. Yeah? Because my x can be, see this pencil line, Johannes? So x can be all of these values and all of these values. It just never reaches 0. 0 not included. Same with y, right? Y is going to be the same. Negative element of the reals. Y, any real number, the only number it can't be is 0. So I know you knew the wing graph before, the reciprocal graph, but now those are the parts. And so all of those characteristics will be part of any rational graph. So any graph with an x on the bottom. Now, I think you'll agree asymptotes are a little weird, but asymptotes make rationals super easy to graph. They'll end up being really easy to graph, right? I see Eileen nodding. Your head. They look weird at the beginning, but because they give you so many different pieces, you'll notice that the asymptotes kind of give you guidelines where you draw your picture, right? A graph will never, ever, ever cross a vertical asymptote. So it's all like little boundaries where you keep your sections in. Notice what I said before. If you've got a section of your rational graph, the only tricky part is they're in sections, right? Either 2 sections, sometimes 3. I have to erase this because asymptotes will always travel towards the asymptote and never ever touch it. So asymptotes can be your friend, right? We just have to be able to identify them. So you'll never have a piece of the graph lying on top of another one. So if I've done this section here on the bottom, I know I can clearly move on to the next section and graph the next section. A graph will never ever cross the vertical asymptote. It can't. Otherwise, it's not a function. And 99% of the time, it won't cross a horizontal either. There's the occasional time it crosses a horizontal, but not usually. Okay? So they actually end up being not that difficult to graph. And again, I think what I might do is I'm just going to go to the textbook for a minute. I'm just going to, if you read it, great. If you didn't, I just want to take a quick look at the textbook, and I want to highlight a few things. So on page 113, just because it gets a little more technical than I'm talking in class, and it says, recall that an asymptote is a line that a curve is just a function, approaches but never reaches. The word asymptote comes from the Greek word asymptotos, meaning never meeting. So they talk about vertical asymptotes, which are vertical lines, which correspond to the zeros of the denominator, right? For example, if we take the rational, now is this a rational function? Yeah. Polynomial on the top, polynomial on the bottom. If there's x's on the bottom, we know it's a rational, and it's going to have, they're not all going to look like sets of wings, by the way, but there'll be some curves in there for sure. So if we take this rational function, we can't have a denominator of 0. So you know how we figure this out? How are you going to figure out the zeros of the bottom? Well, factor, right? Factoring will give you those zeros. As soon as we identify what x can't be, you know that those are the vertical asymptotes. So this means this one has vertical asymptote at x equals 6 and x equals -1. Okay, and sure enough, this one's a little hard to read, but here's vertical asymptote at x equals 6, and this one is a weird one. This is x equals -1. Okay, so that's all I want you to focus on today, that are at this beginning part. Factor the bottom, that'll give you your vertical asymptotes. Okay, they've used a graphing calculator here. Let's just look over here. I just want, and they have shown you, and I'll talk more about horizontal asymptotes in a minute. Horizontal asymptotes are not like verticals. The graph can cross and touch a horizontal asymptote. So just keep that in mind. 99% of the time, though, they won't. Okay? So here, this is really hard to see, but the graph crosses at right here. So this graph, this didn't have a vertical asymptote. We're going to talk about that in a minute. This graph actually crosses right here. Now, we say that y equals 0 is the horizontal asymptote, because you can see that the graph is trying to, like, it's running really close to the x-axis. It does cross it, but then it just starts running close. That's a really weird graph. It's not really a really interesting graph to study because there's not many parts to it, but that's just to show you that they can, not very often, but occasionally cross a horizontal asymptote. I'm more interested in looking at this, okay? Let's take a look at this one a little closer. Is this a polynomial function? Does it fit the requirements? Is this a polynomial on the top?
No.
Yeah, it's a linear. Is this a polynomial?
Yes.
So it's a rational function. Why doesn't this have a vertical asymptote? Why doesn't this have, it has x's on the bottom. How do we find our vertical asymptotes? Yeah, does this one factor? No. Well, let's see. Basically what you're doing is you're setting the bottom equal to 0, right? And you're solving for x. So let's try that. X squared plus 1 equals 0. Because that's all we did here, right? You just set this whole thing equal to 0, then you factored from those values. Okay. So what's the deal here? X squared equals -1. So x has to equal the square root of -1. That's why, right? That'll never happen. So that means there are no unrestricted values or non-permissible values for x. And it's because of the x squared, right? No matter what number I put in there, it's always going to be positive. So this number is always going to be positive. Adding a 1 is always going to be positive. There's never ever going to be a 0 on the bottom. There's no way I can ever get a 0 on the bottom because of the square and because of the plus 1. If that was a minus sign, that would be completely different, right? But because of the sign, so very occasionally you're going to get a polynomial that's kind of, it's a little strange. There's no non-permissible, so that's okay. It means there's no vertical asymptote. That's why it's just going to look like this. This just keeps traveling forever and ever this way and that way. Okay? Let's take a look at this last one too. They did two kind of tricky, weird ones. No non-permissibles, right? It's still a polynomial. No non-permissibles. I'll never get 0 on the bottom, right? X squared plus 9 equals 0. X squared equals negative 9. That's not possible. So again, no vertical asymptote. You just end up with something weird again, right? Okay. We are going to come back to figuring out what the rules are for horizontal asymptotes. We're going to work through a few examples, and then I'm going to come back to this section here, and I'm going to give you a few more little notes. It's super easy now, I think, to pick out vertical asymptotes, right? The bottom ones. But the horizontals require a little more in-depth study. So let's just do a few examples that we have in our example booklet. I'm on page 11. Here's a classic rational. It's got the set of wings. It's got two asymptotes, right? So what's the equation of the vertical asymptote? X equals 3, right? Horizontal asymptote would be what? Y equals 1, right? That's the horizontal asymptote here. So X equals 3, Y equals 1. Okay. So if X equals 3 is the equation of my vertical asymptote, that tells me what my non-permissible value is, right? X can never equal 3. That's the value that the graph approaches but never ever reaches, right? So these two are the same value. They're just kind of written. It means X can't equal 3. Well, that automatically gives you your vertical asymptote. All right, domain. What would the domain mean? X can be everything except X can't equal 3. Okay. And the range, Y can be everything except Y can't equal 1. So it's pretty easy picking out these. These are to give you, again, a little exposure to all the different types of graphs you might end up graphing. There's going to be a lot of these guys, right? The wings. And if you notice, if you look at your equation here, the graph was done for you, but notice from the equation, this also can tell you your vertical asymptote, right? You know that we can never ever have a denominator equal to 0, so to figure out your non-permissibles, you can just set your denominator to 0, solve for X. This gives you your vertical asymptote, right? And your non-permissible value, right? I'm going to come back to horizontal asymptotes after we do a few more of these examples. Okay, the next one. What does the next example look like to you? Looks like a linear function, right? Except one little part. What about this? What is this? It's a hole in the graph, right? So, are there any vertical asymptotes? Right? In order to have asymptotes, you're going to have curves in the graph, right? Your graph kind of approaches something, then takes a bend, right? It approaches and then takes a bend because it can't reach that value. I don't see any vertical asymptote here. I don't see any horizontal asymptote here. Would you agree? But I do see a hole. A hole means there is no value at, let's see, x is negative, where x is -2 and y would be -6, right? That hole means the graph is empty there. That point is not included in that infinite set of points that creates the line. So there is a non-permissible value, right? The non-permissible value is x can't equal -2. Okay? I'll also include this. I'll say there's a hole at -2, -6. Okay, so if there's no value at x equals -2, that means my domain can be any real number except x can't equal -2. And range, same thing. Y can be any number except y can't equal -6. Sorry? Why is there a hole? Okay, I'm going to get to that, but I'll tell you why there's a hole. If I look closely at this, okay, it looks like there's, what would you say? Wouldn't you say x can't equal -2 here? Wouldn't that be a non-permissible value? Because like x plus 2, I set that equal to 0, and then I solve for x. X is -2, agreed? So that's my non-permissible value. But why isn't there, can you figure out why there isn't a vertical asymptote at -2, why it's a hole? Is there anything at the equation? Let's take a closer look at this. What do you see in this? This is a polynomial, right? This is a polynomial. It's in factored form, right? Look what happens. These guys are the same factor, right? So what happens is they end up canceling out. So what am I left with? And what is x minus 4? Just a line, right? Y-intercept at -4, slope of up 1 over 1. So that's how the line was created. But I can't forget about this -2. This -2 was part of the original equation. It got canceled out, but it was part of the original. So I graph the line, but I have to include an empty hole here because that hole can't exist. If that value of x actually existed, the whole denominator would become 0 and the whole graph would disappear. It wouldn't be it wouldn't be possible to be graphed. Okay? We're not going to get into the graphing yet though, but we'll figure that out when we're graphing. Okay? Let's take a look at this one. Okay, you know what I want you to do? Okay, make the bottom equal to 0 and solve for x. So what do you get? X equals -2, x equals 1. Agreed? So those are actually my non-permissibles. Because I can't have, like you're solving for x, but just to figure out your non-permissibles. So x can't equal -2, x can't equal 1. Now, there appears to be only one vertical asymptote, right? X equals 1, so I'm just going to record that. What about horizontal asymptote? Is there? I think so, right? At y equals 1? But I noticed there's a hole again, right? There's a hole at -2, 2. Now, where did that come? Because of the common factor of -2, right? Common factor at x equals -2. So this creates a hole at x equals -2. domain XER, x can't equal -2. YER, whoops, I have to go back here. Yep. X can't equal -2 or 1. YER, Y can't equal 1 or 2, right? Because this is where my hole is. Okay, let's take a look at those horizontal. Do you guys have any questions for me, or? So repeat for you. Is this repeat for you? Yeah. Does anyone want to tell me how the horizontal asymptotes come to be? Do you remember this? How horizontals work? Do you remember, guys? No? Okay, let's go backtrack before we do this last example. Let's look at our horizontals again. The very first graph we did was 1 over x, and it had a asymptote of 0, okay? See if you can create a pattern. This was, I'm going to tell you, focus just on the x's. This was x over x, right? 1x over 1x. And my horizontal asymptote was 1, okay? This one, there wasn't a horizontal asymptote, so I guess we can't use that. What about this one? I ended up with x over x again, horizontal asymptote of 1. So it appears I'm having either a 0 or a 1 for a horizontal asymptote. This one, it looks like it's 1 again. I know that's really not much to go by, but can you see any? So we saw horizontal asymptotes of 1 or 0 or none. Any patterns you would notice here at all? Evie? How did we get horizontal asymptotes? Yeah, the coefficients. So if you go back to page 114 of your notes here, so I've written a lot, right in this little section here, this is where they talk about horizontal asymptotes. Okay? So, generally speaking, I'm going to number these. I'm going to say, or I'm going to do a big star here. Generally speaking, if the polynomial in the denominator has a larger leading exponent, so a higher exponent on the bottom than the top, okay? The graph trails along the x-axis to the left and the right. What this means is it has a horizontal asymptote of the x-axis, y equals 0. That's all that means here, the x-axis. So let's just take, I'm going to write this on the board, then we're going to go back to our examples and see if it's true. So basically it's this. If you have for a rational function, if higher power is on the bottom, is in the denominator, horizontal asymptote is y equals 0. So that's like an example like this. Let's see. What if I had y equals like x to the power 5 over x squared, right? And then I might have other stuff attached to it. It doesn't really matter what's attached to it. You're just focusing on the highest powers on the top, the leading coefficients, right? The ones with leading coefficients, whatever the highest powers are. So if I whoops, flip it around. 2 over 5. Okay? If I have highest powers on the bottom, horizontal asymptote is y equals 0, right? If the powers on top and bottom are equal, the horizontal asymptote is the coefficients of the highest powers. That's what you just said, right, Eduardo? I think something like that. So for example, if I have, let's say I have a y equals 4x squared, and I'm just going to go dot, 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 because I don't really care what comes after that. We're just focusing on the highest powers. Over 2x squared, you know what the horizontal asymptote is? 4 divided by 2, they cancel each other out, or 2. Another example, the ones that we just saw a lot of, y equals, we had x squared plus over x squared plus 8. What's the coefficient? 1 over 1, which is how we got a horizontal asymptote of 1. If you end up with something like this, y equals, let's say you had 3x3 over 5x3 plus whatever, your horizontal asymptote will be 3/5. Okay? So, the same powers top and bottom, really easy, they just cancel each other out. Whatever you're left with coefficients, that's your horizontal asymptote. If you have higher on the bottom, it's always going to be y equals 0. There's one more case. What case am I missing? Okay, if highest power, by the way, another one of these guys is just your classic, this one, right? The classic one we started with. Higher powers on the bottom, right? Because there is no power on the top, highest power on the bottom, y equals 0. Okay, last one. If higher power on top. Anyone want to take, we just saw one of those. What about this
y
one?
is not equal to 0.
Yeah, what about this one? Which one did we just look at? Sorry. This one. What happened with this one, the one with the hole? These guys ended up, or what would I have? You could either look at it this way. These guys disappeared. So what was I left with? Did I have anything on the bottom? Highest powers on the top, right? Or look at it in this form. What would x times x be? I'd have an x squared on the top and just an x on the bottom, right? Okay. So what was my what was my horizontal asymptote? What do you have written on your notes beside here? None, right? That's your last case. If highest power on the top, no horizontal asymptote. None. So you either none, or you have y equals 0, or you have the coefficients of the highest power. That's it. So let's go back and test that. Make sure I didn't screw up anyway. Let's go back and look at the notes that you were using, or the examples that we did together. Then I'll let you guys go on a break. Okay. Starting at example 1, do those rules apply? 1 over x, highest power on the bottom, y equals 0. Check. Okay. Let's look at this one. What case is this one? X plus 4 over x minus 3.
The same power.
Same power? So the powers cancel. I'm left with 1 over 1. Horizontal asymptote is y equals 1. Okay, check. Highest power on the top, nothing on the bottom, so no horizontal asymptote. Check. Let's do this one. These guys, you could either look at it two ways, right? You could say it's an x squared over an x squared, or if these two guys cancel, you have an x over an x. So horizontal asymptotes, coefficients, y equals 1. Check. Okay, let's do this last one together now, using our newfound knowledge. What would the horizontal asymptote be without even looking at the picture? X squared over x squared, so y equals 1. Okay, what do you think the vertical asymptotes are? I have to set this equal to 0, right? And then, yeah, and then we have to factor, right? X plus 4, x plus 1 equals 0. So we get our x equals negative 4, x equals negative 1, right, Johannes? Thank you. So those are my non-permissibles. X can't equal, oops, sorry. Why is there only 1 though? Maybe it factors, right? Okay, I guess I gotta factor the top too. Sorry, we'll do one more thing down here. So y equals x plus 4x minus 2 all over x plus 4 x plus 1. Okay, my non-permissible values are negative 4, negative 1. Before you can figure out your vertical asymptotes, I guess we have to factor completely. That's gone. So that tells me there's a hole at negative 4. Okay, so my vertical asymptote, there's only one then. Vertical asymptote at, this is the only guy left, x equals negative 1. Horizontal asymptote we figured out right away. Now they're actually easy to do, right? The horizontal asymptotes. They're easier than verticals, I think. Okay, now the only thing we have to do, we've got our non-permissibles, our verticals, horizontals. The only thing, I figured out my hole, I just have to figure out my y value of the hole, negative. Okay, so that's the coordinate of the hole. You just need all that info for your domain and range, right? So XER, YER, but X can't equal functions. We actually have to eventually pick up a pen and paper and graph them ourselves. That may be a little harder, right? This time we were given the pictures, we were just pulling out the info. But now that we understand the parts, we're going to spend a little more time on identifying the characteristics on your own. You're going to do a few questions. The harder part seems to become when you actually have to produce the graph yourself, usually. Or maybe not. Okay, so go take a break. And when you come back, I'm going to assign you page 115 and 116. And they might have stuff to hand out to you guys. Sorry, Joanna, kept your calculator way too long. I'm also going to give you your tickets today. The number got erased.
Yes, sir.
Hmm?
Yes, sir.
No, I just had the new number though. I got to go get it again. Hi.
No.
Yeah. No, they drew it this morning. Yesterday's number they drew this morning. I have it on the board. I gotta go get it again.